Hello. So in this problem, we are computing more derivatives, but here we are going to need to use the chain rule, right? So chain rule occurs when you have sort of nested functions, functions within functions. And looking at our problem here, right, we have a square root, but then we have an x squared plus 1 inside. So we have basically a function, x squared plus 1, inside another function, square root. So that's why we're going to need the chain rule, okay? So let's recall our chain rule. So chain rule says if we want to take the derivative of something like f of g of x, right? So if we want a derivative of something like this, so we take the derivative sort of as normal of the outside and sort of just let the inside be, right? So the inside just tags along for a ride, but then we have to multiply by the derivative of the inside, okay? So that's what we're going to do here. So we want to compute the derivative of this thing. So this is sort of, this f is not that f, to be clear. So f prime of x here then is going to be, well, I want to take the derivative of square root. So maybe as a middle step, I'm going to write that f of x, I'm going to write this as x squared plus 1 to the 1/2, right? Because that's sort of the better way of doing roots, is to use the fractional power, so we can use that power rule or polynomial rule. Okay, so now if I'm going to take the derivative, then I'm going to sort of pretend the inside is just whatever, like just an x or something, right? I'm sort of ignoring the inside. I only want to take the derivative of the outermost thing. So to do that, I'm going to bring the 1/2 down. The inside just stays itself. And then I'm going to take 1 away from the 1/2, which gets me to -1/2. But now, right, I need that derivative of the inside bit. So now I can multiply, or I'm going to declare, right, I'm going to multiply by the derivative of the inside, x squared plus 1. So now I can do that. So I have 1/2 x squared plus 1 to the -1/2, and then the derivative here, so derivative of x squared is 2x, and derivative of 1 is nothing, right? It gets obliterated, so I just have 2x. Now, as a note, you might think, like, what happens if you go too far, right? Like, what if I looked at this and I was like, but like x is an inner function and the outer function is square, so I need to do another chain rule, right? Well, you could do that, actually, and it would be okay, because if I think of that, right, same thing that I did here, right? I did the derivative of the outside, but then I did, okay, I'm going to multiply by the derivative of that inner function. So if I had this idea, I'm going to do this in a different color, because this is the right answer. I just want to show that if you were to keep going, you wouldn't screw it up, as long as you sort of did everything correctly. So if you were to think of this thing as being some function squared plus 1, well, you'd still do the derivative of that thing, right? So you'd still get 2 times that piece, right? You'd still get 2x. But then, if I thought that x was a sort of thing that deserved a chain rule, well, then it would be the derivative of that thing, x. But here, right, I'm taking the derivative of x, but the derivative of x, this, is just 1, meaning all I'm doing is multiplying by 1, which, like, sure, I could do that. Why not, right? Doesn't hurt anything, right? There's no problem with that. I haven't messed it up. So if you sort of go too far in some sense, it's actually okay. It's not going to do anything bad for you. It causes more work, I will grant that, right? It takes you longer because you're doing sort of stuff you don't need to, but it's okay, all right? So that's that. Hello. So, shock of shocks, another derivative. But again, this one will again involve chain rule. Chain rules are sort of very common to see in exponents, roots, and logs. Those are sort of huge, common places to find them. And sure enough, here we have an exponent. As a note, these example videos are designed both for the first time you see it and coming back and sort of reviewing. So if you haven't seen e to the ex sort of rule yet, don't worry. This isn't us saying like you should know it somehow without being taught it, right? So standard disclaimer. I'm going to proceed as if you have seen it, and you can always sort of come back to this one. Okay, so chain rule, right? So that's saying if I'm taking the derivative of f of g of x, I'm going to get f prime of g of x times g prime of x. Okay, so I'm going to go ahead and do that for this one. So here I'm going to get f prime of x. So I'm going to have the derivative of the exponential, but the derivative of the exponential is itself, right? So this is just going to be the same thing, e to the 3x squared plus 2x times, but now I need that g prime, so I'm going to have the derivative of that exponent, right, the inside function. So this is 3x squared plus 2x, which, to be clear, I still have e to the 3x squared plus 2x, and always a good idea to use parentheses here. I'm going to have the derivative of this thing. Well, bring down the 2, so I get 3 times 2 is 6. Reduce the power by 1, so I get x. And here, 1 times 2 is 2, so I just get 2. And that's it, right? So again, there's no inside function in the inner function, right? I don't have to worry about multiple chain rules, which is a thing. That is a thing that can happen, but I don't have to worry about it here. So this is it. This is everything, okay? So that's that. Hello. So in this problem, we're taking a derivative that requires a chain rule, but not just a chain rule. This is also going to require some other stuff too, right? So there's actually a number of ways that we could tackle this problem. For example, we could expand this out and do maybe like a quotient rule, for example. We could use rules of logs to actually avoid taking a chain rule, but I'm not going to here, just because I want to show the chain rule. And we could sort of rewrite some stuff. In fact, why don't I do that? So I'm going to sort of manipulate this a little just to show the sort of thinking that you can do when you tackle something like this, which is to say that like just because you see sort of a way of doing it doesn't mean that's the only way of doing it, and sometimes it's worth taking a second to look at it and sort of see different ways of approaching and see if one might be easier than another. So looking at this problem, I see that the top of this fraction is just a number. And since it's just a number, I don't have to worry about a quotient rule for this first thing. What I'm going to do is rewrite it as follows. So instead of doing 13 over x squared plus 1, I'm going to do 13 times x squared plus 1 to the minus 1. Okay? Then I'm going to have natural log of x to the 1/2 plus 1. And really, I can rewrite that using log rules to take this power out front. So I'm going to have 1/2 natural log of x plus 1. Okay? So now I can do this by doing a product rule, which will involve a chain rule eventually. So let's see that. So to do a product rule, right, I'm going to have, so I'm going to take this thing, the derivative of that. So this thing is f of x, to be clear. So the derivative then of f of x is, so I'm going to have the first, so 13 times x squared plus 1 to the minus 1. I'm thinking of all of that as the first thing, right? So I'm grouping it like this. Times the derivative of the second. So I'm going to write that I'm declaring it, but I will do it in the next step. And to be clear, I do this declaring step so that you guys can sort of follow along easily. You don't have to do that in your own work. This is just a thing that I'm doing to make it more obvious what I'm doing step by step. So that was first times the derivative of the second, so now I need the second. 1/2 natural log of x plus 1 times the derivative of the first. So that is 13 times x squared plus 1 to the minus 1. Okay. So this thing stays as is. So this is still 13 times x squared plus 1 to the minus 1. Here, well, derivative of a coefficient doesn't do anything, right? The coefficient goes right outside. Derivative of natural log of x, that's 1 over x. So this is 1 over x. And derivative of 1 is 0, so that gets obliterated, right? This is a coefficient, this is a constant, and that's an important difference, right? Derivative of a constant goes away, becomes 0. Derivative of a coefficient, the coefficient just slides out of the derivative and you deal with whatever else is there, which is why it's important it's a coefficient, right? There's something else there. All right. So then I have this thing stays the same. So 1/2 natural log of x plus 1 times. So now I have the derivative of this thing, but this thing is something to a power, right? The 13, to be clear, the 13 slides out of the way because it's a coefficient, but the negative 1 comes in front. So it multiplies that 13 by negative 1, negative 13, and then I subtract 1 from the power. But I had a function to that power, not just x to that power. So then I also need to multiply by the derivative of that inside. This is the chain rule, right? So continuing on then, I could pull all of this out, right? So that I could have like 13 over 2x, just to clean it up slightly. I don't have to do that, but why not? Times x squared plus 1 to the minus 1 plus, this thing stays the same. So I'm going to have 1/2 natural log of x plus 1 times, so then I still have my negative 13 times x squared plus 1 to the minus 2. And then I have the derivative of this thing. So the derivative of x squared is 2x. Derivative of 1 is 0. So there we are. Okay. And again, I could expand stuff out and clean that up more, but why? So unless I sort of have a reason to do that, I'm not going to. So this is my final answer. Okay. And as a note, this is actually really common to see sort of in the middle, right, in media res, in the middle of things, to run into things like the chain rule. So it's a good idea to always sort of keep an eye out for that, because it may not be the obvious first thing that you run into, but it might show up later on in the process. Okay, so that's that.